How many capes do you have?
How many? You can't ask Superman how many capes he has.
Yeah.
That's not allowed.
I mean, I've never actually. You wore a Naruto shirt once? Wait, you wore a Naruto shirt? You wore a Naruto shirt?
A Naruto shirt? That was someone else. Yes, it's true. There are. I've heard. It's true. I have heard rumors that there's someone who looks a lot like me who is seen wearing shirts other than blue, but it's probably not me. It's just some guy who looks like me. So, if you ever see that person in Walmart or something, assume it's not me. It's some other guy. So, let me begin with a word of prayer. Ahem. Hem. I'm going to get an air horn soon, and then to start class, I'll be like the DJ. What's his name there? Anyway, let me begin with a word of prayer. So, dear Father, we thank you for this day. I thank you again for these students. Just ask you to bless our work today. Help us to understand the math we're going over, and help the students to be encouraged if they're discouraged, just to do their best and to try to improve if they're struggling. Lord, in your name I pray, Lord Jesus. Amen. On that note, tutoring is starting. I've not gotten the official announcement to pass on to you guys. Like, they usually send me this thing to announce. That has not happened, but I believe tutoring has started. And there's like 3 different ways to get tutoring for this class. There's like through the universities. There's something through Cassis, I think. Those may be the same. There's 3 different ways to get tutoring. There's like the math department tutoring. Anyway, there's like 3 different options. They allow tutor math 121. I don't know, like, we're supposed to encourage tutoring. I have mixed feelings. Like, it's important for you to try to understand it for yourself. If the tutor is just doing problems for you and you're not actually struggling to learn it, you're not going to learn it. Like, that struggle, it might feel unpleasant, but it's, you know, I'm told that when you exercise, there's like this feeling you get about like this burn and things, and then the muscles grow from that. It's the same with your brain and math. Like, that struggle is the learning. Now, if you never get past the struggle to the point of understanding, I know that's not good, right? So if the tutor is going to help you with that, right, that's fine. But if they're going to do all the work for you, oof, well then you're just going to fail the test, right? I mean, that's no good. Because, I mean, I have suggested that the math professors should take the tests for the students, because that would be the ultimate solution for success rates, right? If you want to have the ultimate success rate in your class, have the professors take the tests for the students, right? And then it's perfect, right? But then you guys wouldn't learn anything, and that would be kind of pointless. So anyway, this is a long way for me to say that I am going to give you some kind of bonus points if you go to tutoring, because like other sections of college algebra are also offering some bonus points for tutoring apparently. So I need to figure out what that looks like exactly, but there's going to be some kind of like one of the two. This is for the one that keeps a log, and there's going to be like you sign in and you sign out, and if you go and do your homework there, then you'll get some small amount of bonus points for it. You don't have to do that. You definitely can succeed and thrive in this course without ever darkening the doorstep of tutoring. Like, I'm doing it to be a good citizen of the math department. We're all doing it, so you know. All right. So you can expect an announcement with details about that sometime soon, all right? Any questions about the course before I get into the examples? No? So you should have your quiz back. So I haven't worked with this grader before, so I have a grader to help me with the quizzes, which is wonderful. And so I've given her my solution, right? And so she looks at my solution, she looks at your solution, and then she grades accordingly. And so like, generically speaking, if you try something, even if it's just totally insane, I think you should have at least like 30% on the quiz, give or take. And originally, she'd given like one person 0, but they took the quiz. Like that doesn't work for me. Like, if you take the quiz, you got something in here. Now, of course, I want you to have it right, okay? But also, as a point of order, you know, if you feel like your quiz has been graded incorrectly, I posted a video with the solution of the quiz, right? So watch that video, look at your quiz, and if you feel like your solution is actually correct, and it's just the grader, for whatever reason, didn't see that your solution is really the same as my solution, for whatever reason she just overlooked it, just let me know. We'll change your grade. It's not a big deal, all right? But I can't deal with that in class, right? So like that kind of question you got to bring to me either like after class or in office hours, okay? Because there's just too many of you for me to deal with like personal grade corrections in here as a general, point of order. Yep.
Are there like partial credit
Yeah.
awarded, or is it just you get
Yeah, there's partial credit.
66?
There should be partial credit. Yeah. So, and I usually encourage the grader to write the score on the quiz. So, I don't know. So like, you guys, it's helpful if I can just hand the quiz back in a stack and you just find yours and pick it out, right? But then sometimes there's an issue of like grade privacy or something if the number is on the quiz. Yeah? So how do you guys feel about that? If the number's on the quiz, would you want me to like call your name out and pass them out one at a time? It doesn't matter? How about I'll tell her to put the number on it, but like put it on the back so that we don't see the name with the number. Would that be okay for everybody? I hope. All right. I don't know. In simpler times, you could tell who was like lowest in the class because they'd be the person wearing the dunce cap, right? So, you know what I mean? There used to be like this practice, like if you're like the bottom of the class, you have to wear this like cap that marks you as the idiot. We have come quite a ways from that idea, I think. I mean, maybe too far. I'm not saying that open shaming is necessarily a good thing, but some people who are like not doing their homework, man, if there was the threat of being openly shamed for not doing it, I think it would change the equation a little bit, right? But anyway, I'm just blathering on. No one's going to do that. And I know you guys have other things to do, but if you're not doing well yet, like if you did poorly on this quiz, then you probably need to like readjust how you're studying the class, right? And spend more time on it perhaps. Ask questions about the things you don't understand, these sorts of things. So, any questions? Now, one of you asked me to do a problem at the start, so let me do that. So someone emailed me and asked if I could do a problem kind of like problem number 5 in your homework. So I'll make that my example 1 here. So I'm going to change the numbers a little bit. 3x plus 2 less than 4x plus 8 less than or equal to 13 minus x. Let's see if we can solve this inequality. Now, just because I write down an inequality doesn't mean it's reasonable. In other words, there doesn't have to be a solution. It's possible that the solution set's the empty set, right? Like, we've seen this with some equations, right? Some equations don't have solutions. Or in other words, the solution set has nothing in it. So, yeah, this one's kind of annoying, isn't it? What do we want to do with this? I think what I want to do with this is break it into 2 problems, all right? So I'm going to look at this piece. Right? I'm going to focus on that piece to start with. So I've got 3x plus 2 less than 4x plus 8. Now, how do I solve that? That's a little bit easier to try, right? So let's just look at that. How about we, yep.
I was going to say you combine like terms.
Combine like terms, right? So,
Minus 3x.
mm-hmm. So that gives us what? That gives us 2 is less than x plus 8, right? If we subtract 3x from both sides, great. And then what? Minus 8 from both sides, I like that. And that gives us minus 6 is less than x. Okay, so minus 6 is less than x is what that tells us. All right? So one thing you can do is make a number line. I don't know why I put this line here, number line, and put minus 6 on there somewhere, right? So this says x is what? It's where? It is greater than minus 6, yeah. So this can be rewritten as what? This is the same as saying x is greater than minus 6, right? So the purple, basically on the number line, is something like this, right? That's what the solution looks like for that half of it. How about the other half? Let me do it in a different color. How about this hideous, hideous Carolina blue? What's that? I went to NC State. Let's see here. So I don't really follow sports, but I know that UNC is evil. You know, literally, not metaphorically. No, it's here. So I don't know. My little sister went to UNC. So then what do I do with this guy? Well, let's do the same thing we did last time, right? Like, let's. So what do you guys want to do? Add x to both sides, or subtract 4x from both sides? What do you want to do? Add x. Adding x is a good idea because that will save us from the trouble of dividing by a negative number, which is always a little bit risky. So I got 5x plus 8 less than or equal to 13. And then what's my next move? Subtract 8 from both sides. And that gives me 5x is less than or equal to 5, also known as x is less than or equal to 1, right? Okay, so where's 1 on the number line? I don't know, it's kind of sort of about here, right? I make a solid dot to indicate that it's included. And then x less than or equal to 1, right? So it goes like this. So like there's two schools of thought on the number line pictures. There's the dot, open dot notation. The other way people write these is like this. Some people would do like a parenthesis at -6, like that, okay? And then a square bracket at 1, and like that. So that's so there's the closed dot, filled in dot, open circle notation for not included, included, or you can use the bracket parenthesis. Like these are two different notations for the same idea, okay? The bracket parenthesis notation is nice because it suggests to you what the answer is, right? Like, let's think about this logically. We're trying to solve this inequality, right? Which is, sometimes this is called a compound inequality. Why is that? It's got multiple parts, yeah. Compound inequality. And so that means we're trying to solve them both at the same time. So we need the solutions must satisfy both the purple and the blue inequalities, right? So what's the solution set? What's that? -6 to 1, right? Yeah, solution is. So if we write it in a compound inequality, we could write it like this: -6 is less than x is less than or equal to 1. But usually, and that describes the solution. The solution set in roster notation looks like this, guys. So here it is. It's x such that -6 is less than x is less than or equal to 1. Now this is the first time I've used quote-unquote roster notation, right? This is so-called roster notation. I don't use roster notation too much in here. I try to focus our attention and our energies on using interval notation. Interval notation for this same set of numbers is -6, -6, comma, 1. And the square bracket indicates that the 1 is included, whereas the parentheses indicates that that -6 is not included. It's not part of the solution set. So that's how I solve a problem like this. Yeah?
So for homework, any of those solutions would work? Or is there a certain one you work with?
Let's see here. In problem... Man, I hope I put instructions somewhere. Okay, at the very start of it, I say use interval notation to express solution set for inequality questions. So, So I decided to put it at the start rather than, sometimes in the past I've written it at every single, after about the 15th time I write, please use interval notation, I get tired of it. So I just put it at the start and let us understand it is our custom. Yeah. Now, hey, if this is a quiz question or test question or something, and you leave your answer as like -6, less than x, less than or equal to 1, I'm going to give you like 90% credit probably. But I do want you to write it in interval notation if I ask you. Yep.
So there's some problems like this on the mission.
Mm-hmm.
We need to include, they don't say they include the graph, but we need to include that or no?
No, you don't have to. I'm including the graph for logical organization. Some people, if they see the graph, it makes more sense to them. Other people, the graph is just kind of an annoyance. I don't require the graph. There are problems in your book which kind of push you towards making the graph, right? But I would like you to understand the number line pictures. That's true. But I didn't require it as part of the solution there. So I just said solve the inequality. And this is like number 5 in the mission. Other questions? All right, let's do 2 more inequality examples, and then I'm going to shift over to the new topic, okay? We'll do two more inequality examples here, just to try to make sure we've got the idea. Example 2. Suppose I'm up against, let's see here, 13 minus 2x, absolute value, plus 3 is greater than, I don't know, 1. How would you, I was gonna, so the camera folks, you already moved it? All right, thank you. All right, so what's the first thing? So the first order of business is to isolate the absolute value, right? So what is this? This is absolute value of 13 minus 2x is greater than what? Subtract 3 to the other side. What do you get? 1 minus 3? Negative 2. All right. So, fun fact. The absolute value of anything is greater than or equal to 0. Right? I mean, this is how absolute value is constructed. It is always a positive number, or the absolute value of 0 is 0, right? It's non-negative. And 0 is certainly greater than minus 2, right? Is 0 greater than minus 2? Search your heart. It's true. So let me rewrite this. We've got, what's that mean? I can make 13 minus 2x, it's automatically greater than minus 2, right? Which x? It doesn't matter. It's true for any x. So the solution to this one, so this is true for all x. So the solution here is minus infinity to infinity. Well, that was kind of, that wasn't very, I mean, it's kind of disconcerting in a sense, because you feel like, does this always happen? Well, no, it doesn't always happen, right? Let me show you the opposite end of this spectrum. How about this? What if you're solving absolute value of 3x plus 17 less than minus 1? The thing is, I could make this whatever I wanted. I could put the x cubed plus 17 times the square root of x minus x to the power 4 plus 1 over x to the plus 2 plus x to the 1 million power, absolute value less than minus 1. It wouldn't be any different logically. There is no way to get an absolute value to be less than 0. So the solution to both of these problems is the empty set. There is no x which will solve that. Not because of what's inside the absolute value, but just because of how the absolute value function is defined, right? So both of these, doesn't matter how complicated it is, if you have absolute value less than 0, the solution is the empty set, which is either this symbol, or you can do like this, or you can also say no solution. Which, in terms of the language here, is kind of a little bit quirky, right? Because the solution is to say that there's no solution. Yeah. Yeah.
How come we're doing that now, but last class, like, we solved?
Ah, very good. Because last class, we had something that looked more like this. We had, for example, 13 minus 2x, let's say, plus 3, greater than, I don't know, let's say 10. Now, we didn't have that literally last class, but we had something more like this. See, the next step, if we make the next step, subtract 3 to the other side, we get what? 13 minus 2x greater than 7. So the difference is we had a positive number, or we were less than a positive number, right? Yeah.
So whenever there's a negative or a zero, the solution is the infinity?
Yeah, if we have a negative, if we're greater than a negative number, the absolute value is greater than the negative number, then the answer is everything works. If we have absolute value less than a negative number, nothing works. Because the key idea here is absolute value is automatically non-negative. All right? Now this one we'd have to work out, right? And let's do that. How do we work this one out? So there are two cases, right? The two cases, according to that theorem I stated last time, right? We either have 13 minus 2x is less than minus 7, or we have 13 minus 2x is greater than 7. All right, and then what? Let's see here. So if I subtract 13 to both sides, I get minus 2x is less than minus 20, yeah? If I subtract 13 over here, I get minus 2x is greater than minus 6. And then if I divide by minus 2, what has to happen here? The inequality has to flip. So we get, dividing by minus 2, I get minus 2x over minus 2 is greater than minus 20 over minus 2. And on the other side, I get minus 2x over minus 2 is less than minus 6 over minus 2, right? Flipping the inequalities. And then simplifying, we have x is either greater than 10, or x is less than 3. So, and of course you could picture that on the number line. Let me do that just for the sake of, you know, we've time at the moment. Let's do it. So it's either less than 3, so that would be like this, or it's greater than 10, like that, right? So these, maybe I should use a different color. I'll use red on this one. My bad. There we go. This one versus that one. So, of course, these are not overlapping, right? So the solution set is the union of both of these subsets. Solution set equals to minus infinity to 3 union with 10 to infinity. So that funny looking, the U is for union. There you go. Yep.
If the 3 were multiplied by the set in the absolute values,
If the, just
it
as,
was the exact same problem as plus sign didn't exist. Can you just
oh, sure. Let's try that one. So,
distribute the 3 and then solve for positive negative 10? Or do you not distribute it from the absolute value?
can I swap, to make this problem more interesting, can I switch the greater than for a less than? Would that be okay? Same spirit of the problem. And I'm going to change that 10 to a 15. I mean, I could leave it 10, but then we'd have fractions. Do you guys want fractions? No? Okay.
Yeah.
Straight, be your own man. That's right. I like it. So what your question was, can you distribute the I mean, it is true. There's a property of absolute value. So if we have like a constant times the absolute value of A, it is equal to, you know, the, well, if C is positive, then that's the absolute value of CA. C is negative. I got to leave a minus outside, and that'll weird you guys out. So let's not do that. So yeah, I mean, I could pull the 3 inside and multiply it through. And, you know, more generally, a property of absolute value is like absolute value of AB is absolute value of A times absolute value of B. So that's sometimes useful, right? That said, I'm more inclined with this problem to just divide the whole inequality by 3.
You can distribute it.
You can distribute. Yeah, I mean, we could. Sure, this would be. I mean, I can do that. So I'll follow your lead. 39, even though I don't agree with it, minus 6x is less than 15, like that. You could do that, sure.
And then you set it with 39 minus 6x is less than 15, or 39 minus 6x is less than negative 15.
Ah, but this is less than. So that's a different story. So remember the theorem. Let me state the theorem again, since I think we forget it. So here's the theorem. If b is greater than 0, then, number 1, the absolute value of a less than b is equivalent to minus b less than a less than b. Number 2, the absolute value of a greater than b is equivalent to a is less than minus b, or a is greater than b. So there's an asymmetry between the less than problem and the greater than problem. The greater than problem that we just dealt with in example 4 requires us to split into cases. We can't view these as a compound inequality because they're not simultaneously true. On the number line, they're distinct cases, not like my first example where we had 2 cases, right? But they could be combined into one case because the x that's the solution is simultaneously a solution for both of the inequalities. Like, that's not the case for example 4. We have to treat these separately. Logically, it's a separate x. This one, on the other hand, is the less than problem. So we can use the theorem part 1 and trade this for the compound inequality, minus 15 less than 39 minus 6x less than 15. And these kind of compound inequalities are much nicer than the one I started with, because these compound inequalities you can solve in one series of steps. The compound inequality at the start of class was weird because we had a different number of x's in each part of it, so it didn't allow us to nicely like just add or subtract things across the whole thing to isolate the x. This one, on the other hand, x is already in the middle. So all we got to do what is subtract 39, right? So I across the whole thing, minus 39, minus 39, minus 39. And that gives me, oh, thank you, minus 54 less than minus 6x less than negative what?
24.
Negative 24? All right. I'll allow it. And then we need to divide by what? Yeah, divide by negative 6. And what does that do? that flips the less than to greater than. Now, if you want to avoid the red step, the flippity-floppity step, there's a way we could have made our life easier at the start of all this, right? Let me finish this before I get back to that idea, though. So 54 over 6 is what? 9. Greater than x, greater than 4. So the solution here is 4 to 9, right? You got to be careful. I mean, I know students will sometimes give me the solution. If you work like this, sometimes you'll be tempted to write the solution as 9 comma 4, right? Which is just technically speaking nonsense, all right? But if I rewrite this, this is 4 less than x less than 9, right? Logically, these are equivalent. But this one directly mirrors what this is, right? One more roster notation, and then I try not to do it too much. But this is literally equal to x such that 4 is less than x is less than 9. So this is the definition of that interval. It's the set of all x between 4 and 9 not included. Yep.
Do we have to write the solution set after on the quiz, or can we just leave it like 9 is greater than x is greater than 4?
I want the answer in interval notation. So you don't have to write solution set equals that. I mean, I'd be happy if you did. But if you didn't, if you just write 4 comma 9 and put a box around it, that will suffice. I know you guys, you're on your phones, like you don't do a lot of writing, right? Nobody's got pen pals they're writing to. Anybody got pen pal? Okay, but you email people, right? So, like, abstract your pen paling. We've got tons of pen pals. We have more pen pals than we've ever had before. We got social media. Yes?
Is there a reason that you flipped it back to 4 and 9 because that's how the problem started? Or, like, why does it have to be 4 before 9 when you're writing the solution set?
Why did it have to be 4?
Why can't it be 9 comma 4?
Oh, because the convention in mathematics is when we write intervals, we have to write them with the left number being smaller than the right number. Now, yeah, there is, in complex analysis, a meaning for this notation the other way, like 4, 9 would be the line segment that goes from 4 to 9, a directed line segment, and 9, 4 would be the line segment which is directed from 9 to 4. So like there is a notation, there is a meaning for it in later mathematics, but it's not relevant to this course, so I just say don't do it. I mean, there are uglier things. The French write this like this. Do you know why the French do this? Because they're weird. No, it's because there's an ambiguity. See, when we talk about XY coordinate system, right? We talk about the XY coordinate system. We go 4 over, we go 9 up. That point right there is 4, 9, right? And the point 9, 4 is like over here somewhere, yeah? 9 over in the X, 4 up in the Y. I mean, roughly speaking. So because there's an ambiguity, is this the open interval from 4 to 9? Or is it the point 4 comma 9? This is why the French insist on this hideous notation for intervals, which I can't do because I don't want to be thought of as French, you know? I mean, I may be part French, but I feel like it's the part of me that I loathe. So, sorry, are any French here? Sorry, no, okay. Probably not, yep. I'm just kidding, we're all created in the image of God, yes. What's that? Oh, this is the theorem. Anytime we have absolute value, if our problem is absolute value of A less than B, we can repackage this as a compound inequality minus B less than A less than B. So here A is the 39 minus 6x. So it's that. Now, all of this said, we could have avoided this unpleasantness of flipping the inequalities by using a property of inequality. You know, there's a really beautiful property of the absolute value function. It's simply this. The absolute value of a minus b is equal to the absolute value. Well, let me get to the. I need a place to write. Let me erase this. What does absolute value do to a minus? It makes it positive, right? So the absolute value of minus stuff is equal to the absolute value of stuff. Absolute value eats minuses. So in principle, I could have done this at the start, right? 39 minus 6x absolute value is equal to the absolute value of 6x minus 39. I could have just pulled a minus out. This is true. And then if we'd done that, we wouldn't have had the minus x step, right? We would have always had 6x rather than minus 6x. So you can do that at the start of problems if you want to get rid of the minus. But okay, enough. I said I was going to do two examples. I feel like I did 6. It's not bad. I mean, it's good for you guys to see, but we do need to talk about factoring, right? You guys like factoring? No? Yes? I know I always felt like factoring was like way easier than inequalities. As a student, I always had this feeling with inequalities like there was just something I was missing, something right around the corner waiting to get me, right? Some kind of like mathematical boogeyman waiting in the shadows, just lurking about, waiting to take my points, you know? So let's talk about factoring. What is factoring? Yep. When we distribute things out of a number we go into? Right. Let's see here. I guess the first question is, how do you multiply? Do you guys know how to multiply polynomials? Are we good on that? Would it be good to have an example multiplying? So let's first talk about multiplying. What if I had, say, x plus 2 times x minus 3? How would you multiply? We do what? X times x minus 3 plus 2 times x minus 3, right? Which is x squared minus 3x plus 2x minus 6, which is x squared minus x minus 6. Now some of you probably didn't do it the way I did it, right? How did I do that? A weird way? Yeah. So what I did was to use the distributive property. So like what I'm doing here is I'm thinking of A plus B times C is, you know, AC plus BC. And my, you know, just to let you, I'm thinking of this as C, I'm thinking of this as A, and this is B, and I'm just using that distributive property for my first step. And then I do what? I use the distributive property again for my second step, and then what's the finishing move? I combine like terms, right? So going back to my initial question, what's factoring? Factoring is the opposite of this, right? Factoring is unmultiplying. How do you unmultiply a polynomial? Right? That's what factoring is. So factoring is when we like start with what we got to at the end and go back to this, right? That's the goal of factoring, unmultiplying something. Right? So let me do another multiplication example. What example was I on? 6, yeah. So you guys can, I mean, you probably have been taught to FOIL it, right? First, outer, inner, last. That's fine, you can do that. I mean, I do that too. Let's see here, so 3x plus 1 times 2x minus 7. So I do this times this gives me 6x squared. Then this times that gives me minus 21x. This times this gives me plus 2x. And then the constants, minus 7. And then we combine like terms, right? So like that is 6x squared minus 19x minus 7. So I think multiplying is actually pretty straightforward, right? Even if it was bigger. So what if you had like, you know, x plus 3 times x squared plus, you know, 10x, I don't know, plus 7. So here's a guide. When we're multiplying something that has 2 terms with something that has 3 terms, the answer, before we combine like terms, has 6 total terms, right? 2 times 3 is 6. There should be 6 things we're adding together. When we're multiplying binomials, which is 2 terms, a binomial times a binomial gives you 2 times 2, which is 4 terms, right? I'm expecting 6 terms, and the way I do it is to use the distributive property. I say it's x times the thing, and then plus 3 times, you know, the x squared plus 10x plus 7. So I don't try to do it all at once. I do an in-between step. I use the distributive property. And then once, these kind of multiplications are really easy, right? Multiplying x by that, what do? We just add 1 power to x each time, right? We get x cubed plus 10x squared plus 7x plus 3x squared plus 30x plus 21. We're not done, right? We still have to do what? Combine like terms. So you know, you just kind of look for it. One of these and one of those. That gives us 10 plus 3, which is, what you got, 13? And where my x is at. Let's see here. 37 plus 37x. The answer is not Texas. Let's see here, 21. So there you go, we multiplied. All right, so multiplication of polynomials is straightforward, but you need to know it, because how do we check factoring? You check factoring by, yeah? By multiplying, right. Factoring is unmultiplying, so the way to check the factoring is to multiply. All right, so let's do some factoring. Oh, I forgot to ask, did we move the camera over? You did a while ago, right? Yeah, cool. Thank you. I don't do well when I try to do the camera myself. I mean, I've tried, and just, unless I'm just working on one board, it just doesn't work. All right. Here we go. Example 9. Factor, if possible, over the reals. All right, here we go. X squared plus 3x plus 2. Can we factor this? So here's what I do. I put a template. I put x here, I put x here. And then I think about, how do I get 2? How do we factor 2 as a number? 1 and 2. I try that. Does it work? Plus 1, plus 2. So this, when we multiply this out, we get plus x, plus 2x, which is my 3x. 1 times 2 is 2, factored. All right, great. Here's another one. X squared minus 4x plus 3. So something like this, like my first order, I try putting x here like that and see if I can figure it out. So you're looking for numbers who multiply to 3 and whose sum is minus 4. Yep. Negative 3, negative 1. Right. Very good. All right. Here's another one. 6x squared minus 19x minus 7. So let's see here. I probably can put like a 3x here and a 2x here. I could try that, yeah? So if I've got a leading coefficient which isn't 1, then I can try to split it into a product of things. Like I could also go with 6x and x, right? There's another possible way to split that, yeah? And 7, how do we get 7? Well, 7's 1 times 7, right? Okay, so let's see. Let me just try something. So like what if I do minus 1 and plus 7? How's that go? I get minus 2 and I get plus 21, which gives me a net of plus 19, right? But that's not what I want. I want a minus 19, right? So just change the 1 to a plus 1 and change this to a minus, factored, right? And this should not be surprising because I just did that over here. So, shall we do another? What if I've got x squared minus 7? Now this is something you might not have done in your previous course. So here maybe I'm teaching you something new, all right? So this factors as x plus the square root of 7 times x minus the square root of 7. You're like, square root of 7, what's that? Well, it's a number. It's a real number. We're allowed to use that in here. So when I say factor over real numbers, it includes the possibility of square roots. So what I just did right here is part of a more general pattern, which is this. A squared minus b squared is a plus b times a minus b. All right? A plus b, a minus b. This is the difference of squares formula. And so all I'm doing in the factoring above, the factoring right above here, is I'm using the difference of squares pattern to factor. I'm thinking of, you know, a equals to x, and I'm thinking of b squared equals to 7, so b is the square root of 7, you know? That's the idea. Now, once you see it once, you probably can do it again, right? Like if I give you, I'll call, we're now to example 10, what do you know? So, you know, if I give you 4x squared minus 9, let me repackage that a bit. That's really 2x squared minus 3 squared, right? So I'm looking at that as the difference of squares. That's a squared minus b squared. Which we can, you know, A plus B, A minus B. Now, once you get used to this, you don't have to write the AB stuff out. You just do it, okay? These are training wheels, yeah? So we've got 2x plus 3, 2x minus 3. You really do not want to use the method that we were using for these ones over here, right? Like this first 3 ones I did with that method, I call this guess and check, right? You write down a template, you guess numbers, see if it works. Guess and check is not the right way to do the last 2 that I just did, because when you have difference of squares, you use the difference of squares formula. You don't have to guess and check, you just apply this general principle of algebra and you're done. All right? So, you notice I said if possible here. Does that mean they're polynomials that what's a polynomial? That just means many terms, right? These are all polynomials. Polynomial is just a fancy term for formulas that look like this, all right? Sums of powers of x's. Example 11. All right. X squared plus, let's say, 4x plus 5. Can you factor that? Yep.
I was going to ask for the formula. How do you choose which one's A and which one's B for the difference of squares formula?
What do you mean? Like how do I know?
Yeah, like
I mean, you just
assign to A, what number you assign to
we just got to recognize that you're looking at a difference of squares. So, I mean, whatever you think of as A, the square of A has to be what you have there to start with. I'm not sure how to answer your question. Yeah.
So that means if the same question was like negative 3 plus 2x squared, the negative 3 could be A.
Let me see here. So your example 10 point, example 10 tilde, you said you had what, negative 3x squared plus 2?
Yeah, no, it would just be the negative 3 plus the 2x. Like, would it ever look like that?
Wait a minute. What was your problem?
I'm just flipping the 2 values.
Minus 9x squared?
Never mind.
I mean,
Negative 9 plus x squared.
minus 9 plus x squared?
Like, so that would the 9 value become A?
Well, I mean, yeah, if we had, okay, I got you. Understood. Let me,
Sorry.
you're fine. 9 minus x squared. Sure, we could do that. And then maybe this helps with your question, right? So for this one, I just think of A as whatever's got the positive sign on it. So like I think of this as being my A squared, which means A is what? 3, right? So this is 3 squared minus x squared, which is going to be 3 plus x times 3 minus x. So yeah, I mean, you can do that. But we do like to have the factors written such that x has got like a positive 1 on it if possible. But I'm happy to have ones like this too, right? If you wanted to have, this one here, some people would be like, well, that's not a good answer. You could also pull a 3 out and a 2 out, and you could rewrite this as like 6 times x plus 1/3 times x minus 7/2. So you could factor a 3 out of the first one and factor a 2 out of the second one and rewrite it like that if you wanted to. I think I'm getting off topic here. Let's go back to example 11. Can you factor it? Yeah.
No.
Why not?
Because whenever I was trying to factor it down my board,
Uh-huh.
I couldn't come up with it.
So everything you tried, it just didn't work, huh? And yet, if I just change this to x squared plus 4x minus 5, that works just fine, right? What do you do on your board?
X minus 1, x plus 5.
X minus 1, x plus 5. But this is kind of unnerving, right? Like, is your inability to find it, is that really a proof that it can't be factored? Or is that just evidence that you don't happen to see? Like, you could easily get stumped on this one, right? So how do you tell the difference between just getting stumped on finding numbers versus genuine impossibility of factoring? Yeah.
This is what I did, or what my teachers have always taught me,
Uh-huh.
is you multiply the first term and then the last term, and then you, and then you get, when you fact sum those, you get.
Right. So like, just let me put some numbers here. So if we're say this is plus little a and plus little b, right? You're looking for a and b, right? Symbolically, what you're trying to do is you're trying to find a plus b equals to 4 and a times b equals to 5, right? You're trying to solve both of those equations at once, and you're pretty much just looking at whole numbers in the previous course, right? You don't usually even look at fractions, right? Is there a better way? How do you know when you can't factor? I'm going to show you now a method which doesn't involve guessing. A method which will allow you to factor any quadratic, period, with no guessing. Like so many robots, you know, you can just do this. It's an algorithm. It doesn't involve guessing. This is called completing the square. Completing the square is our last best line of defense when factoring gets into trouble. So like when you get stuck on a problem, or you just don't see how to do it right off, complete the square. Here's how it goes. So let's keep it simple in here. We're given x squared plus bx plus c, all right? I'll talk more about the case. What if we had a number in front of x squared? What could we do? Yeah, exactly. If I had 3x squared plus 2x plus 1, I could rewrite that as 3 times x squared plus 2/3 x plus 1/3, right? So if you think about it, if we can understand how to factor when the leading coefficient is 1, then we always have this trick. We can pull the number outside of x and we can factor it out. So if we just understand how to factor things with the leading coefficient being 1, then we can do everything, okay? So let's focus our attention on the nicer case when there's not a 3 out front. Let's focus our attention on this, right? How do you factor this? And how do you know you can't factor it if you can't? What we're going to do is we take half of this and we rewrite this as x plus b over 2. You square it, and you subtract b over 2 squared plus c. That's it. That's completing the square. It's not something we do to an equation. It's something we do to an expression. Some of you have been taught completing the square before where you add things to both sides of an equation. I don't want to think that way because I want to be able to complete the square on an expression. There's no, right? This isn't like equal to 0 and we're finding solutions. We're not there yet, okay? We're just factoring. You notice that? Everything we're doing here past the inequalities material is involving expressions. So we're given a formula in x and we're rewriting the formula, right? So the answer here is, again, a formula. We will later look at setting the formulas equal to 0 and then finding which x's we can put in to make it, you know, true. But that's later, okay? So this is completing the square. Let me put it into practice. So example 13. Well, let's try it out on this one. X squared plus 4x plus 5. What happens when